Microwave sources, microwave tubes, series on microwave engineering, lecture number 4.00. Microwave tubes are amplifiers and oscillators that play a key role, a crucial role in the design and functioning of microwave communication systems. They are used in building both transmitters as well as receivers. Klystron amplifiers, reflex klystron oscillators, magnetrons, traveling wave tubes, etc. are examples for microwave tubes. Ordinary tubes are conventional tubes like triode, pentode, etc. are used in the design of amplifiers and oscillators at low frequencies, but they are unsuitable, unfit for use in the design of circuits to be used at high frequencies like microwaves. They don't work as amplifiers. They don't work as oscillators when frequency is in the microwave band. Why they are unsuitable? Why they are unfit? Why they cannot be used at high frequencies? In the present session, the focus is on providing answers to these questions. In addition, we also discuss about the basic principle based on which microwave tubes are able to provide amplification, able to generate a microwave signal. Several types of tubes got developed. The session concludes with a small brief over different types of tubes and also bringing out any interconnection that exists between them. Now let us move further to the core session. Here we study about the unsuitability of low frequency or conventional tubes for operation at high frequencies like microwaves under several heads. Let us start with the brief introductory points on this subject. The conventional tubes like triode, pentode, etc. used to design low frequency amplifiers and oscillators. They are less useful. Actually, they are not suitable. They are not fit to work at higher frequencies. Specifically or especially above 1 gigahertz, their performance becomes severely impaired. They become crippled because of several reasons. What are those reasons? These reasons are grouped under several heads. First one, increase in tube capacitances and lead inductances, transit time effects, gain bandwidth limitation, increase in power losses, increase in heat generation. We discuss about these 5 heads one by one in a very comprehensive manner. We consider first inductance capacitance effects. Capacitances between tube electrodes and inductance of lead wire become too large for a microwave resonant circuit. Capacitances exist between tube electrodes. Inductance exists for a lead wire, even at low frequencies too. But these capacitances, these inductances, they can be neglected at low frequencies. But at high frequencies, the same capacitances, same inductances, they become too large. They appear, they get magnified abnormally when compared to capacitances, inductances that are associated with the microwave resonant circuits. The real part of tube input admittance becomes large enough to cause a serious overload of the input circuit, nearly shorting the source, decreasing the output power rapidly, ultimately reducing the operating frequency. Inductance capacitance effects can be minimized by reducing the lead length and electrode area, but it leads to a limitation on power handling capacity. To make the first point more clear, consider the expression for resonant frequency of an LC circuit. When frequency is ordinary frequency, smaller frequency, L and C, they assume certain normal values. But when frequency falls in microwave band, frequency is very high, L and C, they assume very small value. A capacitance that can be neglected at low frequencies compared to capacitance in the resonant circuit, it becomes considerable. Sometimes it may become huge when compared to the capacitance in the resonant circuit that is working at microwave frequencies. When it is considerable, then we have to take capacitance, for similar reasons the inductance of lead wire, into account in the design as well as analysis of the circuit. When we take these capacitances and inductances into account, we can find huge amount of deterioration in their functioning. Transit time effects. At microwaves, the electron transit time becomes considerable compared to signal period, and as a consequence, electron oscillates to and fro in cathode grid space, or electron may come back to cathode. It leads to reduction of operating efficiency. At microwaves, due to large transit time, transadmittance becomes complex with a small magnitude indicating decreased output. Consider a tube. This is cathode, this is plate, positive, negative. Electrons get emitted, they travel towards plate. To reach plate, electron takes certain amount of time. It is called transit time. This time is small, so small that it can be neglected when the tube is functioning at low frequencies. But when the frequency of operation increases, time period it becomes small, and at microwaves, time period becomes so small that compared to time period, the transit time cannot be neglected. It has to be taken into account. If it is to be taken into account, or when it is taken into account, we can find that it leads to reduction in the operating efficiency. It leads to reduction in the output signal. Another aspect, gain bandwidth product limitation. Conventional tubes are associated with gain bandwidth product limitation. It is independent of frequency. This product is independent of frequency. Larger gains can be obtained only at the cost of bandwidth, but it is so only in case of resonant circuits. Conventional tubes are tubes we use at lower frequencies. They obey gain bandwidth product limitation. But the tubes that got developed for use at microwaves, their principle of working is different from conventional tube functioning. They employ either re-entrant cavities or slow wave structures. They don't obey this gain bandwidth product constancy limitation. If we use conventional tubes, actually they are not suitable, they are not fit, but for argument's sake, if we use conventional tubes at microwave frequencies, much gain is not possible from them because gain bandwidth product is constant. Bandwidth is usually high because we are operating at higher frequencies. The bandwidth is high, gain cannot be large because of this gain bandwidth product limited. That problem is also there if we use conventional tubes at microwaves. At microwaves, either re-entrant cavities or slow wave structures are used, hence they are not bound by the product limitation. Hence, higher gains over broader bandwidths are possible because new design that is used for microwave tubes. Losses and heat generation. At microwaves, due to skin effect, resistance increases, copper losses goes up, radiation losses and dielectric losses also become large, leading to wastage of power. As losses ultimately appear as heat, rising the device temperature, it may even impair the performance of the device. The losses can cause damage in two different ways. One way is the input which we are giving, it is getting wasted. This is one aspect. Second aspect is the waste appears as heat, rising the temperature of the device. A rise in temperature can cause deterioration in the performance of the device. If you don't want the performance reduction to happen, then we have to see that heat is removed immediately after its generation. Some heat removal mechanisms must be incorporated in the design of the device, but it makes the device expensive. Both the aspects are there associated with losses. Now we spend some time on trying to understand the basic principle based on which microwave tubes are designed. Amplifiers and oscillators. In both these circuits, energy transfer takes place from a DC source into an AC signal. In case of amplifiers, the AC signal is supplied at the input terminals. Energy from DC is transferred to the signal, thereby increasing its strength, and then the signal is delivered at the output terminals. In case of oscillators, energy transfer is into a component of noise that is existing in the circuit. When energy is transferred, that particular component gets energized and then it is available at the output terminals of the oscillator to be taken out for further use. Notice in both the circuits, amplifiers and oscillators, energy transfer is there. This is also true in case of amplifiers and oscillators that work at microwave frequencies like klystron amplifiers, magnetron oscillators, etc. Of course, the technique, the method adopted, used in the transfer mechanism may be different. In fact, it is different. What is the method used or adopted for transferring energy to the signal at microwave frequencies in amplifiers and oscillators? This particular query is answered right now here in the present slide under energy transfer mechanism. Amplifiers as well as oscillators are circuit arrangements which transfer power from a DC to AC. The basic principle based on which microwave tubes are designed lies in electron ballistics. During interaction between particle and field, particle means electron, energy transfer takes place. When the field favors the particle motion, the transfer is from the field to the particle. And if the field opposes the particle motion, transfer of energy is in the opposite direction, resulting in loss of energy by the particle and gain of an equal amount of energy by the field. If the field happens due to a current carrying the signal, the energy transfer to the field strengthens the signal, resulting in the gain. This is the basic principle of functioning of all microwave tubes. In all the tubes, electrons are used. Electrons are negatively charged particles. First, they are energized to higher levels of energy with the help of a DC voltage source. Then these electrons are pushed, they are forced to move against the field produced by the signal. When charged particles move against the field, energy transfer is from electron to the field, which leads to strengthening of the signal which is producing the field. This is the basic principle underlying the functioning of microwave tubes. Now, a small brief on types of tubes, microwave tubes. Tubes can be classified mainly into two categories, linear type or O type tubes. In these tubes, the electron beam travels along the length of the tube and is also parallel to the electric field. Focusing field is parallel to the accelerating electric field in these devices. Examples for this kind of devices are klystrons and traveling wave tubes. Another type is there, crossed field or M-type tubes. Here the focusing field is perpendicular to the accelerating field. Magnetron is an example where focusing magnetic field is axial and accelerating electric field is radial. So O-type, M-type. Under O-type, linear beam tubes type, one can find several tubes. Some employ cavities, some employ slow wave structures. Some employ resonant circuit. Under resonant circuit category, klystron, twistron, helix, TWT, reflex klystron, these are all under linear beam tubes which employ cavities. Cavities are resonant circuits at microwave frequencies. Another category is also there under linear beam tubes, which they employ slow wave structures, forward wave, backward wave. Some employ forward wave, some employ backward wave. Backward wave amplifier, backward wave oscillator. They fall under the category of linear beam tubes using slow wave structures using backward wave. Helix TWT, coupled cavity TWT. These two use slow wave structures. They are actually, helix is a slow wave structure, coupled cavity is also a slow wave structure. They use forward wave. Crossed field tubes, magnetron, FWCFA, dematron, amplitron, carcinotron. These are the tubes that fall in the category of crossed field devices. Broadly resonant, non-resonant, and also maser. Maser is another type which doesn't fall either in resonant or non-resonant. Maser stands for microwave amplification by simulated emission of radiation. Gyrotrons fall under the category of masers. Resonant, standing waves, re-entrant, magnet. In case of non-resonant, forward wave, backward wave. Under forward wave, re-entrant, non-re-entrant. Under backward wave 2, re-entrant, non-re-entrant. Say re-entrant, non-re-entrant refers to cavities. Cavities are basically resonant circuits at microwave frequencies. Two types of cavities, re-entrant cavity, non-re-entrant cavity. This gives a brief description of various types of microwave tubes that are in use. These are some of the things which I want to share with you for right now. To recap, various limitations that are there with conventional tubes for operation at microwaves. They are discussed in the present session. The energy transfer mechanism involved in the functioning of microwave tubes. This aspect is also described. A brief description of different types of tubes, classification of tubes. It is also given. Enough for now. Hope you have a fruitful, a successful, and enriching learning experience. See you again soon in another session. Bye bye.